The last section of this unit is 6.4, which is our second fundamental theorem. I'll give you an example of when we apply it. You're going to see this and sort of presented in two different ways. If we saw this integral, for example, we would be able to come up with its antiderivative, and it wouldn't take us long at all. So what happens though if we have a definite integral for some funky function that we don't know how to derive? Well, when this happens, what we do is we then end up saying, well, that is in fact the function of that definite integral. Meaning maybe we won't be able to say the function is y equals x cubed over 3 plus c, but we would be able to define our antiderivative just using this notation. Meaning, even if I can't antiderive this by hand, that is still a function whose derivative is e to the sine of ln of x cubed. So let's walk through the two different scenarios of when this second FTC is put into place. Here are the two presentations. I would pause and write both of those down. The first one, we've already played around with just a little. Now we're just presenting it in this way, saying, I can define a function as being the definite integral of some other function, right? So that's one, where we then define big F as saying that the derivative of big F is in fact little f. So the second one is where it's different. And folks, I want you to put this, like compartmentalize this, put that second one in a different bubble than the others. Because what this is saying is we don't actually have to antiderive if I'm taking the derivative of a definite integral. Look at the variables and this notation. And then let's do a quick little proof so that it sits better with you. This is saying, if I have this definite integral from a to x of f of t, and I want to derive that definite integral with respect to x, well, that would give me f of x. So let's actually sort of unravel it and then roll it back up so that we can see where this is coming from. So folks, the first thing I'm going to do is just look at that definite integral. And if I were to antiderive this, and the one thing I did not mention is that a in this represents a number. That a is a constant. So if I were to antiderive this, I would use my first fundamental theorem, and I would get that. And I think we'd be fine with that. So now step two is saying, okay, well, let's derive that. And by definition, the derivative of big F is little f. If I take the derivative of big F of a, remember that a represented a constant. So a is a number. So if I took big F of a number, it's going to result in some number. What is the derivative of some number? 0. So that would in fact leave us with 0. But people, we're not going to be doing this step to get to this step. We're seeing that shortcut where all we need to do, and it's a little bit strange, but all we need to do is replace the t with that variable x. I'm going to do some examples with you. So here we go. Here are three different types of problems. So you'll notice for problem 1, I can actually antiderive that. Right? I know that that's going to be t to the 4th over 4 plus c. I'm not going to do that though, because what the second fundamental theorem told us is that that has to be true. So what do I want to do? I want to take that t that's in that function, t cubed, and replace it with x. And that gives us x cubed. So nice and tidy. If you try doing the t to the 4th over 4 and then plugged in the x for t and the 1 for t, and then derive that, you would still get x cubed. All right, let's look at b. What's that going to look like? My hope is that you said that's going to be sine of x over x. So clean and simple. All right, let's look at C. What's different, folks, for C? And I'm hoping that we are seeing my limits of integration are off. That second fundamental theorem tells us that A is our lower limit. So what do I want to do in this case? I want to switch those limits of integration and negate that integral. Now you might be thinking that that dt on the top is a little bit weird, but it means the same thing as 1 over 2 plus root t dt. So just think of it in that same, just the same way we would do with a number. We can put that dt or the dx on top. All right, so now let's work out that problem. Now what am I going to do? Everywhere I have a t in my function, I'm going to replace it with x. So our solution would look like so. Now, they are not all packaged in this way. So here's our next question. So the question we're now asking is, what if that upper limit isn't just x? So let's walk through this, folks. And let's, like we did previously, just focus on the antiderivative and then derive it. So let's see. This would give us big F of g of x minus big F of a. So now I want to derive that. So let's think about what that would look like if I took the derivative of big F of g of x. Start with that. Well, the derivative of big F is little f of g of x. What are we thinking? What are we thinking? Chain rule. All right, if I were to derive that, I would have f of g of x, but then I would have to multiply by g prime of x. Great. So then what about the derivative of big F of a? A is a constant, so big F of a would also be a constant. So that goes away. So now we have it. This looks a lot like the upper limit being x, except we now have to plug in g of x everywhere we have a t. And remember to multiply by g prime. So that is our chain rule. So let's look at that bottom example. So step 1, if I have 5t squared minus 1 over cube root of t, everywhere I have a t, I'm replacing it with x cubed. So it looks like this. I can clean that up in a second. Next, I want to multiply by the derivative of g. So I plugged in x cubed, so I have to multiply all of that by 3x squared. So we could then write that like so. And I can clean it up, but oh, whatever, that's fine. Okay, so they are similar to this. There's only one little twist. And that twist is going to occur if I look at 2b. So let's not start there. Let's start at a and pause it, write it out. And for 2, this is what I'm getting. Everywhere there was an t, I plugged in x cubed. And lastly, multiplied that by 3x squared. I didn't shortcut here. I actually combined, and there is our result. Great. So now, people, when I look at b, I still want you to think about big F of b minus big F of a in this. Before we jump into that, let me explain why we're able to just think about this in the same way that we were working through all of the other problems. So folks, what I have here is I started on this side right here on the left, and I said, instead of going from x to the 5th to ln of x, there's a property of integration that allows me to go from x to the 5th to some value a plus a to ln of x. I can break it up into 2 separate integrals. But you'll notice that the first integral, if I started from x to the 5th and I went to a, that doesn't satisfy my second fundamental theorem, so I would have to switch my limits of integration and negate that integral. So now, if you look at that second step, I just switched the limits of integration from a to x to the 5th, and then I negated. And then you'll notice that that is the f of b minus f of a in the original. That's my OG right there. So what we're going to do now is use our second fundamental theorem and work through this in pieces. So first, if I'm doing my big F of b, it would look like that. Everywhere I have a t, I'm going to replace it with ln of x. So I have sine of ln of x cubed and then chain rule times 1 over x, the derivative of ln of x, minus, and now I do the same thing with my f of a, my x to the 5th. So when we work that out, we end up plugging in x to the 5th for my t. And so we would end up with sine of x to the 15th and then chain rule times 5x to the 4th. And that looks like that. So I don't want us to shortchange the other piece of our second fundamental theorem. And that's when I define a function as an integral of another function. So here my big G is defined as that definite integral from 0 to x of little g. So we are asked in this to sketch a graph of big G. So we're identifying this is my derivative graph right here. That's my derivative graph. Okay, great. Do I have an initial value? Did they give me a value so I could start it and not have a general solution? They did, but it's disguised. The initial value that we know is g of 0. Think about what g of 0 is. Let's plug in 0 for x. That would give us g of 0 equals the definite integral from 0 to 0. Well, what does that give me? 0. So I know one value. I know 0, 0. I found a line, but I didn't know how to make it thinner. So here's my axes. Great. So now let's remember what the derivative is telling us. Talk to me about what's happening with my graph and that interval from 0 to 3. Well, it looks like from 0 to 3, my derivative graph is positive, but it's decreasing. Positive means big G is increasing. The fact that the derivative is decreasing tells me the shape of big G is concave down. So that seems to be the shape up until 3. Now, let's look. 3 is a critical point as well, right? So we know that 3, it's 0, but now from 3 to 5, my derivative graph is still, it's decreasing, so it's still concave down, but now it's negative. So that means big G is now decreasing. Well, and that made sense, folks, because I know that if I looked at this point on my graph, I know that 3 is a critical point. And what kind of critical point? It's got to be a local max because my graph went from positive to negative. That means big G went from increasing to decreasing. Great. Let's keep going. So what's going on from the interval from 3 to 5? Well, from 3 to 5, it looks like it's, oh, we did that one already. So now let's look from 5 to 8. I don't know what's happening. So let's look from 5 to 8. Looks like at 5, that is where there was a little bit of a shift, right? 5 looks like it's a min on my derivative graph. So I know that it was decreasing and the shape was still concave down. But at 5, from 5 to 8, my graph is still negative. That means big G is still decreasing, but it's now increasing, which means the shape of my graph changed at 5. 5 is an inflection point, right? So I know that my graph still decreases, but now it's concave up. Now it's concave up. All right, 8 looks like it's a critical point, but since it doesn't change signs there, it doesn't look like it's a max or a min. So what's going on at 8? At 8, it hits 0, but it's still negative and decreasing. So that means that 8 is an inflection point. Remember where your derivative changes from increasing or decreasing or vice versa? That's an inflection point. So that tells me that at 8, let's say 8 is right there, I have an inflection point. So now my graph has shifted from concave up to concave down. And this is a decent sketch of my big G. And then B, is it increasing or decreasing? Well, I can look at the graph that we just sketched, and I could say that it's increasing because my derivative is positive for those values there. That was fun. So I want to look at these questions for a minute. I put the answers below just in case you look at them and you're comfortable. Just feel free to fast forward. So now let's look, folks. And you'll notice for these, they're asking for big F, F prime, F double prime. So second fundamental theorem. If I'm looking for my big F of x, and that's my integral from 2 to x. Okay, they're asking me to find big F of 2. Well, that means I'm plugging in 2 for x. But look, if I plug in 2, that's going to be my definite integral from 2 to 2. I don't even care what it says in there. That's 0. That's 0. So I know that big F of 2 is 0. Great. So now they're asking me to find f prime of 2. Well, I first need to find f prime of x. So that tells me everywhere I have a t, I'm going to replace it with x. And then I have to plug in 2 to figure out what that is. Plugging 2 in for x, I get root 13. Great. Lastly, f double prime. This is a nice little throwback. We haven't done this in a minute. F double prime of x, I now need to take the derivative of 3x squared plus 1 to the 1/2. So if I want to derive that, I'm going to use the chain rule. And we would end up with that. So f double prime looks like so. So f double prime of 2 means I'm going to plug in 2 for my x's. And we end up with 6 over root 13. That's so great. All right. So see if we can get 5. The first one is clearly 0. The second is identifying, well, what is f prime of x? Well, it's inverse tan of x. So if I'm looking for f prime of root 3, that takes me back to my 30, 60, 90 triangle. And if it's tan, opposite over adjacent, root 3 over 1, and I know that that happens when my theta is 60 degrees, pi over 3. Great. Lastly, f double prime of root 3. Well, what is f double prime of f? F double prime of x. Then that would be, what is the derivative of inverse tan? That would be 1 over 1 plus x squared. So then if I plugged in root 3 for x, I get 1/4. I'm going to end on this just so that we are comfortable writing these expressions for our second fundamental theorem, writing these in terms of definite integrals. So here we are asked to come up with this function f of x if we know f prime is 4 cos of root x, and we know the initial value f of 3 is 8. Take a second. And we should have this. Now you might remember how we came up with those values, where if we know what f prime is, and we know f of 3 is 8, well, we started with this. And then when we did our first fundamental theorem, we said, well, that's just f. I'll use just regular f since that's f prime. So we know those two things are equal. And we plug in that initial value. We know f of 3 is 8. And the last thing we did is we added 8 to the other side when I plugged in what the f prime function was. But we end up with what's in green.